All right. So today we're going to be learning the 3 of Newton's laws of motion. Oh, it's your Lord Jesus. Oh, this is. All right, we're just going to use the old-fashioned board. All right. So, do you remember from Little School Land, Newton's first law?
Is that like where an object is in motion, will stay in motion?
That is the first law.
Okay.
So objects in motion or at rest tend to stay in motion or at rest unless acted on by a net force. Objects in motion. When I write in motion, just assume I also mean at rest. Stay in motion unless acted upon, God bless you, by a net force. Okay, so a couple of I guess one definition here. Where's my red marker? I don't know. A net force, in the same way that you would calculate like your net pay on your paycheck, it's the sum of all the forces. So we have a symbol that represents that concept of sum. Do you know what it is from math?
Oh, is it the E sigma?
Yes, it's sigma. This is Greek uppercase sigma. So that's a symbol that we'll be using from like here on out, so we should know what it means. There's another Greek symbol that we've been using so far, and that's delta. Remember, that means change in. So there are lots of variables, and you'll see when we get to power that there are variables that, like letters that are repeated. Like we'll be using W for a bunch of different things. It's just because there are lots of variables, there are lots of abbreviations, and so there are so many that we can't even use all the ones in the English alphabet. We have to use a different alphabet as well. All right, so let's talk about what, damn it. So every night before I leave for the day, I set my PDFs up. I have everything like set up and ready to go for class the next day. It's like one of the items on my to-do list. And because I know that it takes a hot minute, but this computer just randomly shuts down, and it is just maddeningly frustrating. Yeah, probably from that chess.com. All right, so what is inertia? The inertia of an object is sort of like, it's kind of complicated to think about. Have you learned about inertia before?
Yeah.
So the way that we define it is as the tendency of an object to either stay in motion or to stay at rest. So sort of the way you can think about it is the tendency of something to withstand a force acting upon it. So inertia is morely a concept rather than like a mathematical calculation, but we do have a mathematical way to quantify it. The way we quantify inertia is by using mass. So the more mass you have, the more inertia you have. In the same way that a train is harder to stop than a kid on a bike. A train has an incredible amount of inertia because it's so big. It's such a huge mass. And a kid on a bike is just a kid on a bike. So we can quantify inertia by using the concept of mass. The more mass something has, the more inertia it does have. So the bigger your car is, the more force is going to be required in order to change what is happening to it. Your frame of reference is also important. If you're in a car for a long period of time, you stop noticing being in a car. If you're on an airplane, you stop noticing that you're on an airplane because your body becomes acclimatized to the motion that's happening. Whereas, like, when you're first getting in your car and let's say you are really accelerating very quickly, you put the gas on, like, you feel that, like, force, like you're, like, pushed back in your seat because objects tend to stay at rest if they're already at rest. So your body is still at rest until the force of the car acts upon it. But over time, your body gets used to the acceleration of the car and you no longer notice it. And so the frame of reference is important because it helps us to think about what we're experiencing may not be what we are also observing. So it's kind of like a mind trap. You have to sort of think your way through. Is there anything else? No. Okay. So that is the Newton's first law. Son of a bitch. I'm not sure why this is not refreshing or what's going on here. But I think we're just going to have to stop using it because it's making me too irritated.
So that would look way too natural.
All right, what do we remember about Newton's second law? Do we remember it? Not necessarily. Newton's second law is kind of hard to explain, but we have a mathematical equation for it. Newton's second law is basically force equals mass times acceleration. And so what is that saying to us? It's saying that the acceleration an object experiences is proportional to the force applied to it. So here's another Greek letter. This is lowercase alpha, and this means proportional to. And so what we're saying here is that the greater the force, the greater the acceleration. The smaller the force, the smaller the acceleration. That's what we mean by proportional to. Which makes sense to us, right? The harder we push on our accelerator pedal, the greater force we're going to, or the greater acceleration that we're going to experience. You'll be able to get up to speed faster. You're going to experience a greater force on your body because your acceleration is greater. There's a term for that. It's like experiencing, like, have you heard the term G's? Like if you're on a roller coaster, they'll give you like a G rating for like how many G's you experience. A G is acceleration due to gravity. So that force that you are experiencing like on your body is equivalent to that many gravities. And so if you are going really fast in a car and you experience 2 G's, that's like, you know, that, I don't know how to explain it, but like yes. That's, you're experiencing that incredible amount of force because of the incredible amount of acceleration, and vice versa. Okay, so the sum of all of the forces is equal to mass times acceleration. Or in other words, you can calculate acceleration by dividing the sum of all of your forces by the mass of an object. The more something weighs, the less acceleration it'll experience. That should make logical sense. All right, I know that normally there's no lap sitting, but I would like to do a demonstration. Can I have 2 volunteers for a lap sitting? Nobody wants to do a lap sitting?
A lap or a lap?
No. I want to do it. I want somebody to sit on the chair, but you guys are almost all like the same like mass.
Yeah.
Like this would be effective if we had like a little person in here.
We're the fatties.
All right, Gabe, can you grab the blue wheelie chair, please? We're gonna see if we can get this on the video here. I don't know if we will. We'll just hope for the best. All right, so we're gonna put Gabe sit on the chair. Anybody?
I can help it.
Cameron, come on over. Cameron and Gabe are gonna do a lap sit.
Am I sitting on his lap?
Yeah, sit on his lap. All right, okay. First though, Cameron, don't sit on his lap. So come on off to the side. Ryan, you're going to be the pusher. All right, so stand up. Gabe, spin your chair around so that you're facing the door. All right, now Ryan, I want you to use the same force in both cases. So like, think about how you're going to push off.
Okay. I'll just
Now observe Gabe's acceleration. And then, okay. All right, yeah, that's good. That's good. Now bring it back, Ryan.
Okay.
And just give him one push and then release.
Oh, okay, alright.
And see, and you can push him as hard as you want.
Alright, I gotta make sure the wheels are straight.
Let's not crash him though, because we would like him to play tonight.
Okay.
Yep, lift up your feet. There we go. All right, give him a nice push. And he got to the door, and he had to stop himself so he didn't run into the door. Excellent. All right.
Go into the hallway.
So that's a mass of 1. Now let's double the mass by putting Cameron on Gabe's lap. No freaky stuff, gentlemen.
A little bit of freaky stuff.
Just a little bit freaky. All right, lift your leg. Yep. Oh my gosh. Same push, Ryan.
Yeah, almost like.
Yeah, it went maybe like halfway, maybe less than that.
Yeah.
Excellent, excellent. Thank you for that demonstration. So we have determined that the greater the mass, the smaller the acceleration if this force is constant. And that should make sense to us, right? That's a pretty logical conclusion. All right, so when you're using the second law to make calculations, you have to find the sum of all of the forces. And this can be tricky. So let's do an example from your textbook about this. If you could get a book and turn to page 89, that would be lovely. Sorry, guys. Okay. So let's look on problem number 89. Or sorry, page number 89. Pushing a stalled car. 2 people are pushing a stalled car, as shown in figure 4.5a. The mass of the car is 1,850 kilograms. 89. One person applies a force of 250 newtons to the car, while the other applies a force of 395. He's been hit in the weight room. Both forces act in the same direction. A third force also acts on the car, but in a direction opposite to which the people are pushing. All right, so here's my car. The people are pushing in this direction. So I'm going to say that those vectors go this way. One of them is smaller than the other. And then the force that opposes that motion is bigger than both of them and in the other direction. drawing a picture, even if it's something as bad as this, can really help you to visualize what's happening. All right, so how would we add these forces together? The best way to do this is to use an actual XY coordinate, because it'll help you to think about what the sign of your forces should be. All right, so I'm ready to put my forward forces on the positive X direction. This I'm going to call F2. This one is smaller, it's F1. And then in the opposite direction is my opposing force. I'm going to call that F3. So here I can clearly see that this is negative X and positive X. Now I'll know how to make my sum. So the sum isn't just to add up all the numbers. You have to add up the numbers, but because they're vectors, they have to have a sign that makes coherent sense. So then my sum of forces would be F1 plus F2 minus F3. And I know to do that because, again, it's in the negative X direction. And so I can put my numbers in for this. Force 1 is 275, 395 is force 2, and then 560. And so hopefully you have a positive number. If your number is not positive, what will happen in this scenario? Logan? It would be going backwards, yes. Or it won't move at all. All right, so what do we get for an answer here? 110. So we can figure out then what the acceleration is because we know the mass of the car. And if we had to push this car off of a road, for example, and we knew the distance, we'd be able to figure out how long it would take for them to be applying this constant force in order for them to move their car off of whatever space they're in. But I think what the problem is asking for you is for you to find the acceleration of this. And so you would have 110 newtons divided by 1850 kilograms, which is a tiny amount. 0.0595. So that's a small number, but that makes logical sense because these are just two random people pushing a car. Yes, right.
So wait, why do you have the 560 going to what?
Because in my problem it says a third force of 560 newtons also acts on the car, but in a direction opposite to that in which the people are pushing.
Right. That should be like the car itself. I'm trying to like imagine.
What that force would
Yeah.
be, it would, yes, it would be like static friction. Yep. Because your car, the car tires are meant to grip the road, right? Otherwise it would just slide all wobbly. It would be like a little kid on an ice rink. And so when a surface is frictionless, then you would not have anything to oppose the motion. You'd be able to, so for example, in our little experiment here, if this was an ice rink, or we put some of that lubricating substance on the ground, you would eliminate quite a lot of the friction, and then your same force would have probably sent those two out into the hall. Gabe would have probably crashed into some lockers.
Yeah.
All right, so that's how we solve problems like this. I think that this part is the most essential part. If you don't know how to add your forces, things will get hard for you as we move forward. Okay, so I think that that's all I wanted to tell you about second law. Third law. So there's really only one left. Do you remember what it is? Or is this one of those things we didn't spend enough time on because we learned about the birds for too long?
So we're gonna like something that can't speed up.
No. For every action, there's an equal and opposite reaction. So, when Ryan pushed on Gabe's chair, he applied a force. Gabe's chair applied the same force on Ryan, but in the opposite direction. So, here's Ryan and Gabe in a chair with wheels. Oh dear. So the force that Ryan applied on the chair, so force of Ryan on the chair, is equal but opposite to the force of the chair on Ryan. In the same way that when you, what would be a force that you, closing your locker, you push it closed, you're applying a force to the locker, that as soon as you come in contact with that other object, it will push back on you, and you'll feel that. There'll be like a little bit of resistance there. Maybe you've got something stuck in your locker that you can't actually push it all the way closed. That would be the force that is being pushed in your direction. So it's really important for us to know that this is true, because it's hard to sometimes think that when we are doing something, the object we're doing it to is doing it back to us. And so this is all like a whole frame of reference thing. You just have to get your mind trained to think that this is true. So let's do an example of this on page 90, so that we can understand how to put this into practice. Okay, so on page 90, example 2 says, a man is stranded on a raft. And then it gives us the mass, as shown in figure 4.6a. By paddling, he causes an average force P of 17 newtons to be applied to the raft in a direction due east to the x direction. Okay, so here's my xy coordinate scale. This is positive x, this is negative x, positive y minus y. But now in physics, we're going to have a little bit different of ways of exploring this coordinate system. East is positive x, north is positive y. Okay, so I'm just going to draw what it told me just before. P is applied in the due east direction. Due east means parallel to the x-axis. This is P. Now, when you're drawing these little pictures for yourself, you can do whatever method suits you. So if you want to write 17 there instead of P, that's fine. I tend to use the variables because every time I write down a number, it's an opportunity for me to make an error. And so if I just write P, I feel better about myself. But then it also says that the wind exerts a force A on the raft. This force has a magnitude of 15 newtons and points 67 degrees north of east. 67 degrees north of east would be about this line here. And we're calling that vector A. The degrees is 67. This line is called A. It has a number value. It's 15. But we're just calling it A. All right. So in order to add our vectors, we cannot add them like this. We cannot add them like this because we're not really comparing apples to apples unless we resolve those vectors. Resolving the vectors just means that you're turning them into x and y components. You cannot add them unless they are in x and y components. So that means that if we've got our A, this is A, this angle is 67 degrees. Thing is gonna kill my leg. So how do we resolve the vectors? We just need to turn them into x and y components. So the x component is parallel to the x-axis. And the way that we would calculate ax would be a times the cosine of theta. How do I know? It's touching this line, or this angle curve thing.
What are you
It's-
trying to figure out?
If you're touching this, if your line, this dashed line here, if this is touching the angle, that's the adjacent side, that's the cosine. So that's ax. We need to do that also for ay. This will be parallel to the y-axis. Ay is the opposite side, that's sine. That also has a numerical value that we know, because we know what a is. Sine of theta, we know what theta is, so this has a number. I'm not going to use it yet. All right, so now that I have this information down here, I want to read my question again. What does it say? Ignoring any resistance from the water, find the x and y components of the raft's acceleration. So we need ax equals question mark and ay equals question mark. All right, how do we do that? We are going to break our force into its two components. So here is the sum of my forces in the x direction. Here is my sum of forces in the y direction. Now that I've resolved these vectors here, I can put them back on a new coordinate if I want. And right now, that's what I want. So I've got P here, that's my force of my push, that's 17 newtons. And I now have AX, which I know how to calculate. In the y direction, I only have AY. How do I know? Because I don't have any other arrows except for these two. So in other words, when you are resolving vectors, what that means is to turn all of your diagonal lines into lines that are parallel to axes on the coordinate plane. So I went from this to this. Doing this is not necessary. You could do it in your head if you wanted to. I can't think about spaces to save my life. And so I need to draw it out as many times as I can because I don't get it. You are all better at this automatically than me because I just suck. So if you don't need to draw it out, then don't. But at least to get started, I think you should. Okay, so we're looking for acceleration. And so I'm going to solve for A. That'll be the sum of x divided by m. What's the sum of x? I'm just going to look at all of my parallel to the x-axis variables and put them in my formula. So I should have ax plus p. And I'm going to add both of them because they're both in the positive direction. Yes, Logan?
Can we go to the back?
You may. And then that's divided by m. Now, I just want to finish this off, so I'm going to put my numbers in now. A of x is a times cosine of theta. So I'm going to do 15 newtons times cosine of 67 plus 17 newtons from P. Divided by, I think, 1,300. Is that the math? I never wrote it down on my board.
Yeah.
And that'll give me a number. You can see this maybe. What did I get for that? I got 0.0 176. Meters per second squared is your unit. Oh, we did not talk about the unit for force. It's a Newton. And it is, a Newton equals kilograms times meters per second squared. So sometimes it's also called a kilogram meter per second squared. That's really just a Newton. Now I can do this again for the y values. So AY is equal to FY, sum of FY divided by M. There's only one FY though, that's AY. And so I'm just going to put my numbers in right away because I can do that in my head. 15 times sine, of 67 divided by 1300. That'll be an even smaller number, 0.0106 meters per second squared. The formula for force is not very difficult. I mean, it's just mass times acceleration. And so you might be thinking that this is quite a bit easier than the algebra from those other problems like last time. And that's true. The complicated part is that now there's less algebra, but there's a little bit more physics. This here is where the physics ends and the math begins. Well, actually, you could say that this is where the physics ends and the math begins, because to go from here to here is just trigonometry. And the rest of it is just math. Okay. Third law of motion, any examples more that I wanted to do? We can do example number 4 on page 92. Okay, so this guy says, suppose that the mass of a spacecraft, shown in the picture, is 11,000 kilograms, and that the mass of an astronaut is 92 kilograms. In addition, assume that the astronaut pushes with a force of 36 newtons on the spacecraft. Find the acceleration of the spacecraft and the astronaut. All right, so a data table is helpful. I'm going to say MS is my spacecraft mass, 11,000 kilograms. The mass of my astronaut is 92 kilograms, right? Or is it 94? 92. And the force that the astronaut pushes on the spaceship is 36 newtons. All right, so I can't draw. So here's my spaceship. Here's my astronaut with really long arms. I'm saying that the force applied in the positive direction is the man on the spacecraft. That's 36 newtons. What's the force of the spaceship on the astronaut? Remember that for every action there's an equal and opposite reaction, so it's 36 newtons, but in the other direction. So equal magnitude, equal number, opposite direction. So again, we're looking for acceleration. That's force divided by mass. So let's do the acceleration of the astronaut. So I need to know the force of the spaceship on the astronaut. So I'm going to use my negative 36 newtons divided by 92 kilograms. My little friend here is going to go 0.39 meters per second squared negative. That means he's going to go in this direction. So if he pushes on the spacecraft, he himself will obviously look like he's moving backwards. For the spaceship though, I'm going to use the positive 36 because I want to figure out how the spacecraft will react to the astronaut's force applied to it. But that's going to be a significantly smaller number because your denominator is massive. So it's different by a factor of 1,000. So the astronaut is accelerating 1,000 times faster than the spacecraft, which should make sense because the spacecraft is ginormous. Yes, Jeff?
Should we use, instead of like microwave, should we use like less?
That's up to you. That's a really good question. So Jack asked, should we use west or east or forwards or backwards or the negative? As long as you can show where you have determined your frame of reference somehow in your problem, it doesn't matter. As far as like the FRQs go, they'll ask you like specifically and in what direction. So you could say, in this case, I guess the way I would say it would be 0.39 meters per second squared away from the spacecraft, or in the backwards direction. And this would be in the forward direction. Since there's not really an east or west in space. All right, so I'm going to give you the whole rest of the time to work on the homework. It's not that bad though. So I would like you to do, I think it's on page 123. This is homework number 7. 6 through 10. Let me just take a look at this here.
Is homework 7 due today?
This is homework 7. It would have been due today had we had an extra day before the test.
Yeah.
And so my calendar is mixed up. Homework 7 is not due today. It'll be due next class. I'm sorry about that.
No.
I did not go back in and rechange those.
Okay.
All right, so I think you should have enough information now to answer those questions. If you need help or you want me to do one on the board, just let me know and I will do that.
Can you use it back in time to show that?
What?
Can you use it back in time?
Yes, of course.
Wait, today no.
No. No. Stop.